Great. So for this session, we'll talk about, we're still actually in chapter 8, that is total differential. And the focus of today's discussion is, again, on total differential and the application, which is on utility function, production function, and later on elasticity. So we hope we can at least finish the two economic applications before we proceed with elasticity. Okay, so as an introduction, when you have this function, which is y is a function of x sub 1 and x sub 2, getting the total differential would mean that what is the total effect on the dependent variable? So yung nangyari sa chapter 7 class is that we deal with partial derivatives, meaning that we're getting partial derivative with respect to, let's just say, x sub 1, and also we're getting the partial derivative with respect to x sub 2. So ang nangyayari doon is we're just focusing on one change of these variables, a change of this, and also a change of that. So when you're talking about total differential, when you allow this one to change, what would be the effect on y? Okay, so now later on we'll have three scenarios. We'll have a change of this one, a change of x sub 1 holding x sub 2 constant. What would be the change in y? We also have scenario 2, which is a change of this variable x sub 2 holding x sub 1 constant. What would be the change in y? Scenario 3 would be a change of x sub 1, a change in x sub 2. So we're allowing two changes at a time. Then how will that reflect on y? So total differential class is again a change on y itself as the dependent variable. Okay. Now, by definition class, when we talk about dy over dx, again, we can treat this one as ratios of dy and dx. So you're getting the limit when delta x approaches to 0. So in that case, the whole definition of total differential class, you can check that one on a separate file, which I've uploaded a few weeks ago, or last week actually. So you can just check on this one again, just to have a review on the theoretical basis for differentials. Okay, now I'll proceed to again some examples because I was told that you have a discussion on total differential already in your Math 100. So basically, much of our discussion today is more on the economic applications. So again, when we have this function here, which is y is a function of x sub 1, x sub 2, total differential of y means you're getting the partial derivative with respect to x sub 1 multiplied by a change of x plus partial derivative of f with respect to x sub 2 multiplied by the change in x sub 2. So again, when you're getting the total differential, again, it means that you're getting the sum of the partial derivative with respect to any of these variables multiplied by a change in x sub 1 and a change in x sub 2. Okay, so you will find you will need to get yourself familiar with this one class because this is just ultimately the same when you're getting total differential. So if there's one thing to remember about total differential, all you need to remember is that you're getting partial derivative, then multiply it to a change of x or a change on x sub 2. Okay, now let's have an example. So this one is an exercise, one of the exercises in Xiang and Rena's book. So that's in page 186. So supposing we have here z, a function z is equal to a function of x and y. So again, you have a function z is equal to 3x squared plus xy minus 2y cubed. Okay. Now, if I'll ask you a question, let's just say Jessica Fernandez, what do you think would be the total differential of z here?
Ma'am?
Yes?
0 po ba?
Right. Hold your answer. So again, when you talk about total differential, again, in order to get that one, you need to get the partial derivative of with respect to any of this variable multiplied to the change of that variable. You can just carry out the same process kasi nga, it's just the same for if you're talking about total differential. So when we try to apply this one into this function, what is our total differential of z here? Anyone? All right. So if I may continue class, when you're getting total differential, again, all right, going to the discussion. When you're taking the total differential of z class, again, it would be again getting just the partial derivative with respect to x multiplied to so again, getting the total differential is partial derivative with respect to right. Again, partial f partial x multiplied by a change of dx, which a change of x, and then also adding to the partial f partial y multiplied by dy. Now, because in this case class, we do not have a change in x and we don't have also a change in y, we can just write it there and we can just carry it over. And so the total differential of dz, or let me correct that one, the total differential of z would be equal to this. Okay, so again, I would probably say the appropriate way siguro is again, we have this format. Again, it's just the same all throughout. This is again how we get, or we will be getting the total differential of the dependent variable. So again, total differential of z is equal to the partial derivative with respect to x. Again, coming from this function here, multiplied by the change in x plus partial derivative with respect to y multiplied by dy. Okay, so again, there is really nothing, there's nothing new here that we have introduced. All we did was again arrange it in a format that answers total differential. Do we have a question on how we got total differential for z here? So ang mangyayari later class is we will introduce, or we will have an exercise if how about if may change na tayo for x, meaning we have a value for every partial derivative here and every value for a change of x or y. Okay, so that would be our scenario later. For now, because we only have a function which again doesn't have provide any more details, the total differential for z here, or for the dependent variable, is again only this. Okay, now do we have a question? Again, we are just building on the fundamentals before we look at other scenarios. So it's important na we know that the approach for this one. Question? Okay, so now let's move to an economic application starting with utility function. So in a utility function class, when you have, again, you have these two goods, you have x sub 1 and x sub 2. These are, in utility and consumer theory, you are trying to determine that combination of goods that maximizes the utility of that individual. Okay, so in a utility function class, or getting the total differential of that utility would mean getting the partial derivative with respect of any of these variables, x sub 1 here and x sub 2, and multiplying it to the to its actual change, which is again dx sub 1 and dx sub 2. So when you have, again, right now, in a similar or additionally class, again, remember that the slope of an indifference curve, again, let's go back to this one here. So remember, class, in your consumer theory, that the slope here of an indifference curve is again is brought by this, which is again dy over dx, diba? So indifference curves tells us that you want the consumer to stay as happy, to stay as satisfied as before. So when you are getting when you're getting the combinations of these two goods, x sub 1, x sub 2, you are holding utility constant. So when you're holding utility constant, you will need to make sure that the consumer stays on the same indifference curve. So you are just changing combinations here. Your utility does not change at all. And in that case, class, the slope of the indifference curve is again equal to dy over dx, which is just the ratio of your marginal utilities. So to write it, your marginal utility is just a partial derivative with respect to again, of these goods here. So that's a negative partial u partial x sub 1 over partial u partial x sub 1. Now, this is a negative because, again, as you recall your indifference curve, it's a downward sloping curve, meaning that you will need to make some trade-offs in order to, again, to attain one good. So in this example, again, as a review, if you want more of x sub 1, you will need to give up a portion or give up some quantities of x sub 2. Kasi nga, the point is you want the consumer to be as happy as before by staying on the same indifference curve. So going back to the discussion proper, again, the ratio of marginal utilities or the ratio of the partial derivatives with respect of any of these goods is just equal to the negative ratio of your marginal utilities mux mux sub 1 and also over mux sub 2. So collectively, class, the ratio of this one is called marginal rate of substitution. So again, when you go back to theory, this is again the marginal rate of substitution, meaning the trade-offs that you will be doing just to make the consumer as happy. Now, how do we, why are we talking about this one? Because again, relating that if you're holding utility constant class, obviously, if you this would be zero later on. Kung yung scenario is you're holding utility constant, the change in utility obviously would be zero kasi nga you're allowed any of these changes here would bring no change at all sa utility. Again, utility is constant. In total differential class, the possibility is that you can change this one here. You can change your consumption of x sub 2. And the question is, how will that change affect your total utility? So we are now allowing our utility to change here. So let me just go back to that one. So in this scenario, because we're allowing our utility to change, we're now jumping off from one indifference curve to the other. Now, you're in this case, you may consume more of x sub 1 and consuming more of x sub 1, how will that affect your utility? So in this case, this is now this is what we call total differential class. Delta U means delta U is just the same with du here. Okay, so again, what is the change in your total utility when you add more, when you consume more of good X? And as you can see in this scenario alone, that there is no change at all for X sub 2. Kasi nga, did we have a change? We can still consume here the same X sub 2 when we are at point B. Okay, so the point about here, the point about total differential is again, what is delta U class when you allow changes in any of these consumption. Okay, so now going back, going back here, we have our utility function, which is equal to 2x sub 1 plus 9x sub 1 x sub 2 plus x sub 2 cubed. So the idea here is that we don't have much details about the changes in any of these variables. All we have is a utility function. So to get the total differential is just the same as, again, getting partial derivative first, multiply it to the change in x sub 1, and add it to the partial derivative with respect to x sub 2, multiply it to dx2. So because we don't have much detail, eto lang yung this would be our total differential. Okay, so you see class the similarities in terms of obtaining the total differential, but again it is obvious that the theories behind every function here, depending on what is in study. So again, this is utility function. Obviously, it refers to the consumer theory. Okay. Now, before I proceed to the production function, do we have a question again on how we can obtain total differential? You may want to raise them now because again we will try to extend the analysis of total differential later. So far it's clear. Now let's go to production function class. Again, this is another economic application of total differentials. So as a review, when you have production function, it is a Q is equal to is a function of capital and labor. Now, we were also introduced in chapter 7 that when you're getting partial derivative with respect to K and L, you will get this. Okay, you can when you have MPK, it means that you're only allowing K here to change and you're holding L constant. So in that case, we can write it this way. Now, but just to emphasize na we are just holding L constant here. So we can write it here, K and then here. Okay, here. So MPK means that a change in K, a change in K here, and then we are holding L constant. We also have our MPL. So again, MPL is the rate at which output changes with respect to labor with capital held fixed at K. Okay. Now, let me also sharing and then go back. Okay, now I'm sharing again my file here. So supposing class, we now have again a production function which is equal to Q is equal to 4K raised to the power of 3 over 4 times L raised to the power of 1 over 4 here. So again, when you look at the coefficient class, you're now considering a Cobb-Douglas production function. We also noted that K there is 10,000 and L is 625. So how did we arrive at this number? Remember class that wage times L and rent times capital. Okay, so with the values being with the values given here, class, what is output Q? Meaning, what is the level of output when your capital is equal to 10,000, and what is the level of output again when your labor is equal to 625? So you may want to write down your answers. I'll be waiting for your answers in the chat box. What is Q there? Let me also write this one. So what is Q? What is the level of output when, again, initially, these are our units, or this is our, L and K. I'll be waiting for your answers in the chat box. Well, it's a good thing we're only 5, so I would be waiting for 5 answers. Okay. So we already have one correct answer. We'll wait for the others. That is correct. We'll wait for 3 more. So we're currently around 5 people. So I think we'll just wait for 3 answers just to be representative for the class na lang. So we'll wait for 1 more and then we can proceed to the next slide. Okay, how about the others? We are waiting for at least 1 answer before we can proceed. Now, again, u there, or again, given those values, k there, or no, q would be 20,000. Okay, so how did we arrive at that number? All we did was to substitute the values into the production function. That's how we arrive q, which is again equal to 20,000. Now remember these numbers, class, or remember these figures, because later on we will be changing k, we will be changing l, and we'll be changing and we'll be getting, we'll change k there while holding l constant. We're also going to change l later and holding k constant. And scenario 3, we're changing all simultaneously yung inputs. Okay. So again, let me know if you have a question there, because again, these are important, especially when we will be doing approximation later. Okay. So now the next day, the next agenda is that we will need to get first, we'll need to get MPK and MPL. Now, again, as I mentioned, class, this is the standard way of doing it. Now, when there is no values. But if you have values already, class, again, it might tend to be a bit complicated. But again, all you have to do is to substitute those values. Okay. So again, I put this, I put the given on the side. And again, these are just the guide for you. So we answered this one earlier with my ECON 106B class, and I think we can just go ahead and discuss what we did. Okay. So again, MPK is just partial F partial K, again, multiplied by KL here. So again, KL is again if we would have a change in any of those values K and L. Okay. So again, the next thing that we did is again get the first partial derivative with respect to K. We're holding L constant, and so our answer there is 3K raised to the power of -1/4 times L 1/4. And we also wrote on the side our K L here are combinations of inputs. So we have 10,000 and 625. Now, these numbers, class, now these combinations of inputs, these are our initial values. We are still not allowing any change at all into the production. And so again, the values that you're seeing here are those that no change have happened at all. Okay. So again, I am just again also rewriting on this side. I am rewriting MPK. So again, rules of exponent, you can just carry this one on the, down, and then you'll have a positive 1/4 as an exponent. So that's your MPK now is equal to 3L raised to the power of 1/4 over K raised to the power of 1/4. So again, I carried this one to the denominator. And then also I wrote down on the side our inputs of our combinations of inputs. So the next thing that we did was, because we have values already, we can just easily substitute all the values for K and L, and thus arriving us at 1.5. So what do we mean by 1.5, class? This is our exact value for marginal product of capital. So it's only mean that that's the so that is we're trying to estimate here the change in output that is due to a 1.5 increase in capital. So later on, what would be again the change in the output when we allow a 1.5 increase in capital and holding labor constant? Okay. Do we have a question, class? So again, MPK, but by the definition of it, that is again holding labor constant. We're just allowing capital to change. Now, let's also do the same exercise. I think we have time here. Okay, we have a question. Where did the 3 and 3K raised to the power -4 comes from? Now, remember, class, that when you're getting MPK, it means that you are getting it from the production function, right? So that's 3/4. That's 3/4 times 4, and your answer is 3. So that's 3K. And then 3/4 minus 1. So that's -1/4. So you're getting the partial derivative here with respect to K and holding L constant. So that's how you got 3. Okay. Other questions, guys? Okay. Sige. We'll resume, or we'll pause the recording, and we'll do the same for MPL. Okay, so we have one correct answer. Now let's go over to the answers, class, or let's go over to how we obtain MPL. Okay. So again, it is just the same exercise with MPK. But then again, now the scenario is that we're holding capital constant here. So we're only allowing L to change. So the first thing that we did was, again, using the production function, that's 1/4 times 4. And then also owing also to the rules of differentiation. So that's n minus 1. So that's 1/4 minus 1. And so you have MPL here. Okay. Then the next thing that we did as well was we also put this one on denominator just to have a positive exponent. And so we also carried over here, we also wrote down the initial units for capital and labor, which is 10,000 and 625. Okay. We also did simplified here, and since again the values are already substituted, then we get an answer which is equal to 8. Okay, so now in this case, class, diba, when we go back to the definition of MPK, sinasabi natin na we allow a 1.5 increase in capital. We are also allowing in this case labor constant here, and for MPL we're allowing an 8 unit increase in labor. Okay, so if there is if we're holding labor constant. Okay, so now question about how we arrive at those answers before I proceed to the next one. So again, obtaining MPK and MPL is first getting the first partial derivative with respect of any of these inputs, capital and labor. And then we also now substitute the values that are given here on the side. Question? Okay, I hope that is clear. Now, let me just go over on the next one. Okay. Now, okay, here. Okay. So in this first scenario, I mentioned earlier, class, that we'll work on 3 scenarios. So scenario 1 is we're only allowing capital to change here and labor is constant. So if you increase capital by 1.5 units, okay, so let's just say, or let me rephrase that one, okay? So in this case, class, scenario 1 is we've allowed an increase in K of 10 units. So again, it's positive 10 there, indicating that we will be adding 10 units to the 10 units to 10 units to the production. And so how will we try to estimate Q there? Okay, so on this here class, okay, this is again would appear to be familiar to you because this is our this is part of the format or the formula for total differentiation. Okay, so remember class, in our first introduction is that total differentiation is just again total differential. Let me correct myself. That's total differential. Okay, getting the first partial derivatives with respect to a change in x, also partial derivative with respect to y, and a change in y. Now, in this case, class, again, because we have examples already, that is MPK. Again, MPK is our partial derivative with respect to K times that change in K plus MPL times the change in L. So in this first scenario, yung nangyayari is that we are only adding 10 units to capital, in capital, and we're holding L constant. So what happens is that there will be 2 methods to do it. Okay, the first method is this one. Okay, so again, we start off with our initial output, which is 20,000 plus 1.5. What is 1.5? That is again your MPK times 10. So times 10, ito yung change, which change ng K, or this is DK. And your output is equal to, or your output now is equal to 20,015 or 20,015. Okay, so that is the first method. Again, but the point of the total differential is getting an approximate class, a good approximation when you allow changes in any of the variables. Okay, when you go back to the definition class of total differential, again, you need to have an parang small infinitesimal change or a good approximation of the changes. So when you go back here, so 20,015 could be considered as not a good approximate, but in this case, this one is your actual, or is considered as a good approximation to the total differential Q, meaning ito yung actual change ng Q if you will increase 10 units, K of 10 units into the production. Okay, so do we have a question on how we arrive with 20,014.998? Again, this is the second method already, and this second method is appropriate for our definition of total differential. Do we have a question, class, of how we arrive with 20,014.998? Okay, for a while class, just let me just clarify. I think I'll just write down for the sake for those who are not here. So that's 10. Okay. Now again, let me just separate this one. Okay, as method 1 and method 2. Again, and also okay. So this is our second method, and I'll put that one on the side. Okay. Just to bring clarity to my notes. So that's the second method here. And then here, what we did was, again, okay, so again, this is our second method class. As you can see, this is again a good approximation compared to the first one. So this is our total differential for Q there. Okay, so but again, owing to the first scenario only. Okay, now, all right, so time check, it's 11:17. Now, let's I gave this one as an additional credit for for as an additional credit. So can just if you need point if you it's up to you if you want to receive additional credit, but again, all you need to do was to is to give a correct answer for these two two other scenarios. So scenario 2 is what will happen if we reduce our labor by 2 units. So in this time class, you will need to treat capital as fixed and labor constant. So in that case, the inputs or the production now has units that are 10,000 and 623. So again, saan nanggaling yung 623? We reduce again our labor by -2 points. So again, it's now equal to 623. So I want you to give me the actual approximation, or to give me a good approximation, meaning method 2, when again you have when labor is when we allow labor to change. Now scenario 3 on the other hand, class, is again what would be the value when what would be the total differential of Q now when we simultaneously allow changes in capital and labor. Okay, so I think because we have more time, we now have time compared to my other class. So I think we just do it for like maybe 15 minutes for this session here. Sa kanila kasi binigay ko as an assignment kasi we don't have much time. But now, class, you may want to do it now. I think I need to first need to discuss these slides before we go to elasticity. Okay, so I'll stop the recording already, and then I'll wait for your answers. Okay, and that would